Well, hello. I'm going to be showing you, this is part two of, this is the second video. If you haven't already seen part one, this should make absolutely no sense. So you're going to want to make sure and look at part one of that. And we are looking at um, question number two. And so picking up where we left off, we know that the velocity initial of blue is 1663, and I went ahead and filled in the velocity final of blue is 16.63 meters per second. And here are some things that we know about the velocity of the red car. We know that its initial velocity is 25.88, and its final velocity is 0, which may or may not be relevant to us. And its acceleration, do we know that? Well, yeah, we do. It does list it in the information that it originally gives us right here. So in fact, it is 4.77 meters per second per second. So we do know the acceleration there. So the thing that we've got to try to do is we've got to try to figure out, using this information that we have, how on earth we can solve anything when we bear in mind our four main equations. So when we're looking at our four main equations here, that should be meters per second. I apologize. When we're looking at our main equations here and we look at this, on the blue side, all we have are velocity initial final. And on the red side, we have a velocity initial, velocity final, and an acceleration. So if we start looking here, what you have to realize our secret is knowing that since D's are the same and T's are the same, if we use either one of any of these equations, we can substitute into a system of equations, and if we solve for D, we can put in the place of one of these others. So what does that look like? Well, I'll show you here. And specifically, when we're looking at this, it's probably worth noting that if you think about when these cars are passing, we actually don't care where the red car is when it comes to a stop. So I would say that we really are better off almost to eliminate that piece of data as something that it doesn't really matter, because these cars are going to meet before that ever happens. So this could almost be said to be a red herring. So if we start looking at this, is there any equation that has velocity initial, a velocity, in this case, velocity initial, velocity final? This really isn't that relevant to us because it's staying at the same. So that could almost not be something we worry about in the terms of here. And then we have distances and times. And it pretty quickly emerges when you look at that this equation right here is probably going to be our best bet, because it's got distance, it's got time, and it's got acceleration. I'm not saying that none of those others would work, but I'm saying that this is an obvious one that I know will work. I'd have to think about those others, but I'd have to think about it. And so if we do that, we use this equation and we put in what we do know for the red, that would turn into this. So we could say that the distance of the red would be equal to its initial velocity times time plus 1/2 AT of red squared. Likewise, we could say the same thing over here for blue. That should be a B. Now I show B here for times, and maybe this is, let me zoom in a little bit so you can see those a little bit better. I show a B and an R for the time. The truth is, since we already established that the times, these are equal to each other, really, I'm just going to say, well, let's just get rid of those. Time's the same, time is time. We don't have to worry about that. Now also, since we said, and this is a big deal, that distance of blue and distance of red are the same, well, if I wanted to take distance of red, since these are the same, this is the same as this, and this is the same as this, well then I can take this and put it in the place of there. And that's what happens when you do a system of equations. And I'll show you what that looks like. There you go. We can actually cut that out of the way, and then we can scribble this out. And we can say that this of the red, should probably clarify, sorry, this is of the blue, is equal to this of the red. And so let's track that down a little bit more. So I just rewrote this, cleaned it up a little bit, but so you can see where that's coming from. And I'm going to go ahead and plug in all of these numbers that I do know. So here are just the numbers put in place there. We have the velocity of the blue car, unknown time. Blue car's acceleration is 0. Sorry about that, I'm back now. So we can start doing some basic algebra here and start eliminating some things and simplifying. So here we've progressed down, and so we arrive at 1663t equals 2588t plus 2.385t squared. And in typical format, I just now noticed I made a mistake. If we remember way back from the beginning, our acceleration was in fact negative. I did not show that sign as being negative here. I should have. That would make also this negative. And next step is we can subtract 2588t from both sides. We end up with negative 9.25t equals negative 2385t squared. At this point, I'm going to multiply both sides by negative 1. Just go. That will look like that. Of course, we're getting very close. At this point, we can divide both sides by t, which gets us to there, and then we can divide by 2.385. Oops. Need to show my work. We end up 3.88 equaling t, and of course, if you remember at the very beginning, we fed in things like meters per second squared. So of course, our final unit of time, we could go ahead and put that in, would be seconds. So 3.88 seconds is equal to our time. And let us hope, after all of this, that in fact we are right and that this works. Let us see. Thank goodness, there you go. Thank you, and I hope you've enjoyed this episode of Fun with Physics.